Remember to mute your mic.
It keeps tripping in and out.
All right, so in the PDF, we have a reaction. All right, so I showed you today how to calculate or how to determine the order of reaction from experiment using a table.
This is a 20 and 10 to make 30. So if I'm doing CN2 plus, what's that give me?
Remember to mute your mic.
Go ahead. What do you notice about CN2 plus? What do you notice about CN2 plus? CN2 plus.
All right, so before I started, remember I told you today that you may not always get some simple numbers. So where you see like the rate it move from 5 to 10 or from 5 to 15, and you know that it triples, right? All you need to do is divide the bigger number by the smaller one, and you can see how much it goes up by. So 15 divided by 10, that is 3, so it will go by 3. Use the same method here, and you will know if the rate goes up by a factor of 3 or not. All right, so this is the experiment. So, those are the experiments. And the first question, let me just look at it. So it says from the table, use the information from the table to deduce the rate equation. So use the information from the table to deduce the rate equation and calculate the overall order of the reaction. But before we answer that, just tell me what is the order of reaction with respect to S2O8 and I minus.
Sir, we're not seeing because somebody is speaking and their name come up.
You can pin, sir.
I think it's 1.
What happened?
There's 1.
Sir,
Yes.
sir, iodine is second order.
All right, so somebody said I minus. All right, iodine is second order. All right. And what about S2?
That
Oh,
is first
First.
I
order.
think it's 1/3, first order.
all right. S2O8 is first order. All right, so for the persons that says the iodide ion is second order, tell me how you got the second order.
Sir, because the concentration doubles and the rate quadruples.
Which two experiments you use?
1 and 2.
1 and 2.
All right, so you use 1 and 2 because for 1 and 2, this was kept constant, right?
Yes, sir.
And then you double this and the rate, it went up by a factor of how much?
4.
That is correct. So from comparing experiments 1 and 2, the rate of, we double the concentration and the rate increased by a factor of 4. That is a second order reaction. If you double the concentration and the rate goes up by a factor of 4, second order. All right. What about S2?
If I rinse alone, it don't make no sense.
Which two experiment?
You would
No,
use
I'm
2 and
serious. If I
3.
rinse alone, it don't make no sense.
You use 2 and 3. They're going from 3 to 2.
All right, so you use experiments 2 and 3.
3. And I went from
Alright.
3 to 2.
So for experiments 2 and 3, we decrease the concentration, right, by a half. So 0.15 divided by 0.075, and that will be equal to 2. But we are, whose mic someone is? All right. So we're decreasing the rate, we're decreasing the concentration from 0.15 to 0.075. So we're decreasing it by 2, or we cut it in half. What happened to the rate? It also decreased by
We cut in half.
Exactly. Right. So we cut the concentration in half, and the rate was cut in half.
But sir,
Yes.
sir, could I go the other way too? Like, could I start going from experiment 3 to 2?
From experiments 3 to 2?
Yeah, because I did it that way, and then I
Sure.
said that I said double.
Right. Yeah, man. So
Okay.
if you use it this way, you double the
That's the
concentration.
same thing for the rate.
And it doubles.
Yeah.
So whatever you did to the concentration, the same thing happened to the rate. So it
Okay.
doubles. So which order is it when it decreases? No, it's not really saying decrease. No, what you're doing, you're looking at what happens to the rate in relation to concentration. So to know the order of reaction, remember, we look at how the rate changes in relation to how the concentration changes. Remember, for zero order, the rate is not affected by the concentration. For first order, we said that rate is proportional to concentration, meaning whatever you do to the concentration, the same thing will apply to the rate. Yes, I'm going to post it after class. Right, so when you look at the table, right? So if you are seeing it for the first time, what we do, if we want to know the rate, not the rate, if we want to know the if you want to know the order of reaction with respect to this, you are going to look for two experiments where you change the concentration of this, but these must be kept constant. And the person, they use experiments 2 and 3, because if you look at experiment 2, the concentration was 0.5, and for experiment 3, it was 0.075. Also, which is very important, for experiments 2 and 3, this was kept constant. So that is how you choose your experiment. You want to know how this affects the rate, you change the concentration, but the other one must be kept constant. Next thing I do, how did the concentration change? One was 0.15, the other was 0.07075, right? That means the concentration changed by 2, right? So if you look at it from this point, 3 to 2, it doubled. But if you're coming down, it cuts in half. But it changed by a factor of 2, right? Now come across to the rate, because we are trying to see how the concentration affects the rate. Same experiment 2 and 3. 5.65 times 10 to the minus 5 divided by 2.8 times 10 to the minus 5. Basically 56 divided by 28, that is 2. All right. So the concentration, it doubles, the rate, it doubles. That means it's proportional. So when it's proportional, it's first order. So that is how we know that it's first order with respect to S2OA. So we've finished with S2OA. It's first order.
Sir,
Yes?
we're not supposed to divide both twos.
Please repeat.
Sir, where you have the 0.15 divided by 0.075, I get 2, and you
All right.
divide the rate, I get 2. Are we supposed to like divide both of them to get the 1?
No. What we're doing, we're showing that for the concentration, it changed by a factor of 2, and the rate, it also changed by a factor of 2. So we are showing that both of them change in the same way.
So you can pin your screen, please.
Please repeat.
Can you pin your screen, please? Because every time when somebody talk, I can't see.
You have to do it for yourself. You can't do that.
Well, actually, you can, sir. You can.
Oh,
I'm not seeing the icon on my thing.
you pin your screen.
You just need the person who wants it pinned just need to tap the screen twice. Tap your video twice.
All right.
Thank
All right.
you.
All right, so let's go again. We need to know how the rate changes in relation to the concentration. That is how we're going to determine the order. So if you look, the reason why I divide it, right, is because we need to know how we change the concentration. Did we double it? Did we triple it? What did we do? All right. So 0.15 divided by this, you get 2. So it means that we change the concentration by 2. You can go ahead if you have a question. When you divide the rate, the answer is 2. What that means, the concentration, when you change it by a factor of 2, the rate changed the same way. So whatever you did to concentration, the same thing happened to the rate. So that is what we mean by proportional. Whatever you do to concentration, the same thing happened to the rate. Is it any clearer?
Yes.
All right. So let's do the working out for I minus now. And it's the same principle. 2 experiment now where we change the concentration of I minus.
1 and 2.
Right. But also remember, so what if you use 1 and 4? You could use 1 and 4 as well. So for I minus, check this one. So this, if you use 1 and 4, because that person is correct, if you use 1 and 4, they look at 1 and 4. We change the concentration of S2O8, but the concentration of I minus is the same. So all we need, someone might, class, just remember if you're not asking a question,
Yeah, let's stop, Mama.
to
Mama,
my
don't make them get involved.
Jesus.
Sir, I have a question to ask.
Give me a second.
Okay.
So, remember to mute the mic if you're not asking questions. All right, you can go ahead with your question now.
Okay, so could you please repeat what the second rate states?
I should repeat what?
What the second rate states?
Oh, but the second rate,
The second rate? Yes, sir, states, because you know the first one states that, yes. So what would the second rate be? Because the first rate says that concentration is directly proportional to.
Oh, you mean second order? So it's second order, not
concentration is proportional to.
not
rate?
second rate. All right, assume do this second order. It's second order, right? So it's not second rate, it's second order. All right.
Okay, sir.
All right, just but for this one, we are doing experiment 1 and 2. Not experiments 1 and 2. We are to use experiments 2 and 3. But someone asked, what if we use experiment 1 and 4? So I was saying it wouldn't be a problem. Because for experiment 1, the concentration is 0.15. And for experiment 4, it is 0.075. But also, the concentration of this in experiment 1 and 4 stays the same. Now, for experiment 1, the rate is 1.4 times 10 to the minus 5. Let's just change it as a 14. All right, because both of the exponents are the same. So we can say the rate is 14 for experiment 1, and it is 7 for experiment 2. And to make this easier, 0.15, we can call it 15, and we can call this 7.5. All right? So going from experiments number 1 to experiment number 4, what did we do to the concentration?
Decrease it.
We decrease it, but you have to tell me by how much.
Divided by 2.
All right, so we decrease it by a half, right? Right, if you divide it, you will get 2. But looking at it going from 15 to 7.5, we drop it by a half. Going from 14 to 7, you will get 2. If the numbers are the same, people, it means that both of them are changing in the same way. Both the concentration and the rate change in the same way. So it's first order. The reason why I'm doing this is so that you can see that both the concentration and the rate is changing the same way. If you don't want to divide first order. Look, if dividing it is confusing, it's fine, you don't have to. Once you look at it, right, you can see that 0.15 to 0.025, it decreased by a half. Right? So we decrease the concentration by a half, going from experiment 1 to experiment 4. when you decrease the concentration by a half, we have to come and look at how the rate.
Yes,
We have to look at how the
yes,
rate
yes.
change. Guys, if you're not asking a question, do your mind. When you're going to experiments, one,
Yes.
experiment
Frida.
four.
Rory, mute your mic, please.
When you're going from experiments 1 to experiment 4, how did the rate change? Did it double, triple, drop by a half? How did it change? That is what we need to know. How it changed? So I'm asking. If it start with 1.4,
It go down by a half.
exactly. It wouldn't be 1.4, it would be 14. So the rate decreased by a half. Good. All right.
So
So the concentration decreased by half. The rate decreased by half. So whatever
so it is directly proportional.
directly proportional. And once it's directly proportional, it's first order.
First order.
Right.
So can we hear about the second order?
Yeah, man. So that's it for the first order, and that is how we got it, right? So for first order, the rule is
So I'm not hearing you, sir.
sorry, a call was coming in. A call was coming in, sorry. All right. So let's move on now to I. So for I.
I put the phone and do not disturb.
Repeat. All right, so for I minus, we're going to do the same exact thing again. Choose 2 experiments where we change the concentration of I minus, but keep this concentration constant. So which 2 experiments can we use for I minus?
1 and 2.
Which other 2 experiments can we use?
3 and 4. 3 and 4.
Right, so we can use experiments 1 and 2 or experiments 3 and 4. So for experiments, come on, sir.
Sir, what I want to know is when you're choosing the concentration, is the bigger number you must put at top as well?
If you put the bigger one, it's easier for you to see how it change.
Sir, I don't hear.
Please repeat.
Sir, I didn't hear what you said.
No, I'm saying if you put the bigger one at top, it's easier to get a whole number to see how it changes. So if you put
thank you.
What? Yeah. All right. So in experiments 1 and 2, how did the concentration change? All right, so this topic, we're doing rates of reaction, but specifically order of reaction. So you have to be able to calculate the order of reaction. So you will get a table, or you may get a table, and you have to look at the table based on how the concentration and the rate changes. You should be able to tell if it's 0 order, first order, or second order. With 0 order, the rate does not change, even when you change the concentration. All right? So for this one now, how did the concentration change?
It doubles by increase by 2.
It doubled, correct. All right, let me just point out this. So we're not going to the exam, right? Let's see for a second order. if the concentration doubles, when you double the concentration, the rate increases by a factor of 4. It goes up 4 times. So for second order, if you double the rate, it goes up 4 times. If you triple the rate, it goes up by a factor of 9. So whatever you do to the, here what, when you go on the exam, right? Whatever you do to the rate, so in this case, right, we double the concentration. Just put it in a bracket. When you square that, whatever you do to the rate, not the rate, sorry, whatever you do to the concentration, if you square it, whatever answer you get, that is how much the rate should go by. So for a second order, we say that the rate is proportional to the square of the concentration. But when we say that, most students don't really get it. So what I'm saying now, for second order, whatever you do to the concentration, you take the square of it. So if you double the concentration, 2 squared is 4. So when you double concentration, if it's a second order reaction, the rate must go up 4 times. If you are to triple the concentration, 3 squared, that is 9. The rate should go up by 9. So for this one, when you double the concentration, what happened to the rate? Wait,
You go 4
1.4.
times faster.
Yes, 4 times faster, right? Does that sound like a second order reaction? You double
Yes,
the
sir.
rate,
Yes, sir.
Yes.
you double the concentration, and the rate goes up 4 times. So when it comes to I minus, it's second order. And when it comes to this one, it's first order. And to prove our point again, right? Let us use experiments 3 and 4. So how did we change the concentration?
Half.
So we decrease it by a half. And what happened to this?
Because the rate go up by 4, man. You hear me, sir?
Right. So the concentration, yes?
Sir, were we supposed to divide the 0.50 by the 0.25?
All right. If you do that right, you will get 2.
Yes, sir.
All right. And what will happen here?
With the concentration,
Divide the
All right.
the rate, sir, the rate will contribute.
if you divide the bigger number by the smaller number, what answer will you get?
4.
4.
Yeah.
So what I was saying, right? When you have the, so like when you go from experiment 3 to 4, and the bigger number comes first, you divide by the bigger number, because when you do that, you will get a whole number, which is easier to interpret. So here, the difference in concentration is by a factor of 2. The difference in rate.
Sir, I'm
here
not getting 4. I'm not getting 4.
Yeah, I got 2.5.
2.5.
Hold on, 7 divided by 2.8.
But
2.5.
20 divided by 7 are 4. Right?
28. Hold on. Divided by
The same power them have, so you don't even have to do the power. Just divide 28 by 4.
by 7, you mean? No.
Yeah, by 7. 7, yeah.
7 4 is 28, right? So at that moment, right, aren't all of them decimals?
So is it 2.8 or is it 28?
No, it's 2.8. No, we were saying that, right? Even though it's a decimal, these exponents are the same. So you don't have to treat it as decimal. You could just say 28 and 7.
Yeah.
Sir, so the exponents always be the same or it can be different?
Please repeat.
Will the exponents always be the same or can they be different?
No, it can be different. All you
What
need
do you
to
do
do
in
is,
the case it's different? What do you do in the case when it's different, sir?
please repeat. Hold on. If
What do you do in the case when the exponents are different?
no, you're going to still see how it changes. So all we need to do, even if the exponent
No, use
changes,
the calculator.
yeah, and see how much it changes by. So that's what we need to see. What is the relationship? So when you change the concentration, what factor does it change it by?
Sir,
Yes? Go ahead.
sir, but why when we divide the 7.0 times 10 to the negative 5 by the 2.8 times 10 to the negative 5, we get 2.5.
Just a second. 0.5.
But sir, when you
But sir, how we know which one them bigger, like the the decimal something?
2.5.
Wait, so we did this already. So 7.
But sir, I'm gonna put the 2.8 times 10 to the negative 5 over the 7.0 times. I get the first sir, but not the other way around though.
So we do 2.8 over
You
7.
did something wrong, sir.
Sir, me
You
get
did something
first
wrong with the
or?
poem.
Sir, if you're gonna call it
Hold on,
28, you have to change the
Let
form.
me check the question. Let me see if we make any mistake with the numbers.
It should be 0.7.
It should be?
0.7. When you divide it by 0.7, you get 4.
All right, let me just check the PDF and see if I made a mistake.
Probably 2.8 should be to -4 and the 7 should be to -4.
Probably. Let me just check. Oh, a -6. This is not -5, -6.
Oh.
All right, so try it now.
You can look after me still.
Yeah.
Yeah, I get 4.
4 you get now.
Yeah.
Yeah, so it's my mistake. Right? So everybody good now? So this decreased by a factor of are 2 ways. Sorry, what topic are we covering? Rates. All right, if you're okay with dividing and getting an answer, that's good. Or you look at the concentration, we drop it by a half. So let's go again. From 0.5 to 0.25, it decreased by half. All right. Now, if you decrease it by a half, and it's a first order, not first order, second order, how much should we divide it by?
Sir,
How much should it decrease by?
sir,
Yes?
I'm still not getting the 4.
You're still not getting the 4? All right, let us see.
Sir, I'm not get the 4 neither.
Give me a second. No, make it no. 2.8 export to the -5.
Sir, shouldn't we use the 7.0 divided by the 2.8, use the bigger number to divide the 2.8?
Just a second. Remember, we just changed the exponent. You know? This is -6. This is -5. So the 2.8 is the bigger one.
Yeah, because 6 are the more negative, so it'll be the smaller one.
Yeah, man. So this is -5.
It's like you'd have -1 bigger, and -3. Yeah.
Thank you, sir. I got it.
All right. So just remember, right? When you get the reason why we are dividing, we have to see what factor it changed by. So you do it two ways, all right? So first, let's work with the order it is in, going from experiment 3 to experiment 4. So going from experiment 3 to experiment 4, we decrease the rate, we decrease the concentration by a half. For this one, how much it decreased by, that is what you need to know. It decreased by 1/4, right? So you drop the rate by a half, and this basically decreased by a factor of 4. You see that? Everybody understand this?
Yeah, we
Yes,
see, we
sir.
see.
Yes, sir.
So if the concentration decreased by a half and the rate decreased by a factor of 4, then it is still second order, right?
Second order.
Right. Good. Now, the next way, if you always divide the bigger number by the smaller one, you will not get fractions. So 0.5 divided by 0.25, the answer is 2, right? So we change the concentration by 2. And if you divide 2.8 by the 7, the answer will be 4. And remember we said that if you change the concentration by 2 and the rate changes by 4, it is second order.
Second order. So we can work it out anyway, right? The decimal and the whole number. Okay,
Just
sir.
work it the way that is easier for you or best for you, all right? So whichever way you understand how to work it out, stick with it. All right?
Okay, sir. Yes, sir.
So when you get your answer, you have to compare the two of them so that you can see the relationship. Once you get that, it's good. So we see that this changed by a factor of 2, this changed by 4, so it is second order. Any question? If you don't understand how to interpret the table, because more than likely, once rates come, you will see a table.
Sir, what about a table where like you have one reactant or one thing and nothing at all is in contact?
There's a next question like that as well, and we are going to work it. All right,
Okay,
so I'll go like that. All right, so the question was, use the information in the table to deduce the rate equation. So what is the rate equation? Based on our answers here, what would be the rate equation?
Rate is equal to K.
All right, so rate is equal to K.
S2O8.
So which of them a second order? I a second order?
Yes.
And S2O8 a first order, right?
Right.
Yes, so that put bracket the I put the square upon it.
Put square.
For
Yeah,
second
so
order.
remember, right? Remember, we always put the order of reaction at the top. But if
Yes,
it's
sir.
third order, we don't need to put the one. All right. So that is our
Well,
rate
I mean,
equation.
if you want, you can.
Yes.
Sir, you
it's
can repeat?
not a problem.
So how would you write a zero order?
For zero order, because for zero order, the concentration does not affect the rate. The rate is just equal to K.
Okay.
Right?
So suppose them the S2O8 was zero order and I was second order. How would you write?
All right, so if the S2O8 was zero order,
Yeah.
that would have been your rate equation. Rate is equal to K times I minus squared.
Sir, what if
Wonderful.
you write the S2O8 and we'll put like 0 outside the square? That would be incorrect.
No, it's not incorrect, but you don't need to put it in here. Once it's zero order, you just leave it out.
Okay, so thank you.
Because remember, I just said that this is the rate equation for zero order. So there's no reactant there. All right, so when it's zero order, leave it out. So it's only first order and second order that appears in the rate equation.
Sir,
Yes?
would it possibly be because a number raised to the
Answer, I'm going
zero
to get you 0.
is 1? A number raised to 0 is 1?
1.
So it would just be 1K
That's
basically.
correct.
So it would just be, oh.
Right. If you're confused, you can ask the question now.
When you were writing the first rate equation, I was not seeing the screen. Could you please go over how you did it, please?
All right, so the rate equation is just rate is equal to K times the concentration of the. So the general rate equation, I'm going to put the general one on the board. So rate is equal to K, A to the M, where A is the concentration, M is the order of reaction, B to the N. So this is a general rate equation. Rate is equal to K, A to the M, B to the N. M and N, those are the orders of the reaction. So when they ask us to, yes?
Sir, the M thing that you were saying that is the order, isn't that they said that the M doesn't determine the order of the reaction, you have to find it, like something like that?
Yeah, man, that is what we just did. You have to use experiment to determine the order of the reaction. Now I'm saying this equation here, this is not the answer for the question, you know. I'm saying that this is a generalized rate equation. So when we do this, that is where we're going to replace M and N with actual numbers. So for this one, that is why for the answer now, we have S2O8 2 minus. It's first order, so we don't need to put a 1. And then for the I minus, it's second order. So you put the 2. So as we just said, M and N, they are the orders of the reaction. So that is why when you calculate the orders, you put it at the top.
So you know that, excuse me, how you know that the I minus was the second order?
You just came in, just checking.
Yeah, I just came in.
For that, all right, let's just hurry and do this. You change the concentration, we look at the concentration of I2, we realize it doubled, and the concentration and the rate, it increased by a factor of 4. All right, this class is being recorded, so if you missed it, it's going to be posted, all right? Yeah, we can't answer everybody for you. It's being recorded, so once it's completed, I will upload it, all right? And you can see it. So let's continue. All right, so it's time now to calculate the rate equation. Have you ever calculated the rate equation? All right. So
Yes, sir.
So we're going to calculate it now for the overall order of the reaction. So we're going to use rate 2. If you're asked to calculate the order of reaction, this is what we will do. Rate 2 over rate 1 is equal to K2 over K1. We are going to do the S2O8 first. And so you're going to pick any experiment. All right, so if you want to use experiment, 2 experiments.
Yeah, what is this calculating?
The order of the reaction.
The overall order.
Yeah, that's different from the overall order.
No, man, what we just did, all right, we just look at the table and determine that it's second order and first order. They specifically asked us to calculate it. So when they say calculate, you have to calculate. You're going to see that we get back first order and second order.
Sir, so this is the calculation that we just did though.
No, man, we don't do this. No, this is when you're actually doing a calculation. So what
Hold on, what you're calculating the overall order of reaction?
So if they say calculate it, you actually have a calculation where you actually calculate the order of reaction.
Interesting. Want to see this?
So
Yeah,
that is what
sure they're working.
that is what we're doing. So for yes,
How many orders are there?
please repeat.
How many orders are there?
We do 0 first and second order.
No, I'm saying like all together. So how many different orders do you have?
Three overall.
Okay.
For this level, we do those 3. All right. So 2 experiments. Experiments 2 and 3. So for experiments 2, the concentration of S2O8 is 0.15 divided by, all right, writing it like this. S2O8 M2 over S2O8 2 minus M1. All right. It's not hard, it's simple. Let's just do it quickly.
What are we calculating, sir?
Sir, so what have to do this?
Yo, I'm on mute right now.
Just give me a second. It's all we're doing is just putting in some numbers. It's nothing to worry about. So rate 2 from experiment 3 is 5.6 times 10 to the negative 4. Rate 1 is 2.8 times 10 to the negative, not 4, negative 5, negative 5. So that is rate 2, rate 1. So what we are doing, we are dividing experiment number 3, experiment number 2 by experiment number 3. All right. So it's the rate from experiment number 2, rate from experiment number 3. The constants will cancel each other. All right. So we go to the concentration from experiment number 2, which is 0.15, and then the concentration from experiment number 3, which is 0.075. If you divide this by this, how much I get? 2, right? All right.
So what the K stand for? Concentration?
No, man, remember K are the rate constant.
We calculate the rate constant?
No, them cancel.
Ah.
Yeah.
Okay.
So this is a past paper question.
Yes, it is a past paper question.
So what did you say this working out is for?
No, look, just pause a second. Look, if you look at it, it's very simple. All you say, you just read, you're looking at experiment 2, dividing everything in experiment 2 by experiment 3.
As some do it still, sir. I get what you're saying. As some do it still, the mathematical way.
Yeah, all right. And this, you would get 2 again, right?
So first order.
Moment, right? No, guys, not guys, everybody. When you reach here, people do maths, them know. I don't do K maths, right? But when I say 2 equal 2 to the M, just say log 2, just do it here, don't multiply it. Log 2 is equal to M log 2.
Just me, sir, them now remember that.
So M is equal to log 2 over log 2. And the answer is 1.
Sir, could you please?
All right,
Sir,
so
I
yes.
got 2 to the M again, please.
Remember up here, M was done exponent M2. It was at the top. Right. So it's still up there. But it's some mathematics, right? But just don't worry about Yes?
Yeah, you don't have to log. You can just say
I'm
2 to the
sorry, but
1
I don't
or 2 to
understand.
the.
Sir, I don't understand it at all.
All right,
Sir,
let's
what
take a
was the
look at
question,
what
sir? What were they asking us to find?
we are to calculate the order of the reaction. Let's say M is 2 divided by 2 and we get 1. We're good? We now reach where for now.
Yes, sir, that is better.
All right. Look, you can be asked to calculate the order of the reaction, so I'm just showing you. All you need to do is divide the two experiments, the rate from each experiment and the two concentrations. That's just it enough. Nothing else. Because if you look here, it says 5.6 divided by 2.8. So it's rate divided by rate and concentration divided by concentration. It's like 2 lines.
Sir, so what are the K's for the K2 over K1?
Those are the rate constant.
Sir,
Yes?
sir, this is like the other way we can just add the like I say add the M and M plus N, sir. When I get the other fraction.
If it's the where you get
Yeah.
1 plus 2 is equal to 3.
Yes.
No, if they
Check
ask you to calculate. All right, hold on. Just give me a second, because I need to point out something to you. If you're in the PDF, right? The same PDF file. I'm going to come back to this question a second. I'm going to come up with this question. But there's a next rate question, because I needed to see that you have to be able to calculate. So there's
But
a
sir,
next.
isn't the same thing that we were doing before? It's just that you have the K2 divided by the K1 and you cancel them out. Isn't it the same thing that we're doing over? And then it just shows how to use the log to show that it is first order. That is all I see. I don't see a difference.
Yeah, it's somewhat a difference from
From what we were doing with the table. Like it doesn't really, it's not a difference. You're just writing out, oh, you get the answer.
basically.
Okay.
So when they say calculate it,
Yes.
that's the way, all right? But I have a next one. So, all right, SO2, Cl2. But this one is not like experiment 1, experiment 2, experiment 3. So you have the concentration, right? And you have 0.45, 0.39, 0.34, 0.28. And all they gave you is the rate. So they gave the concentration and they gave the rate. So 1.35 times 10 to the negative 4. 1.17 times 10 to the negative 4. 1.02 times 10 to the negative 4. 8.4 times 10 to the negative 5. And the question is, use the data in table 1 to calculate the order of the reaction. So how would we calculate the order of reaction for this?
Pick 2 concentration.
Pick 2 concentration and pick
2 rate.
just like we did here. All right. So if it comes where it's not like experiment 1 and experiment 2, and you have to calculate it, this is what you will do. So you pick 2 rate. So let us do it. Let us use 0.45 and 0.39. So what would we say? Rate 2 over rate 1. So it would have been what? 1.35. 1.35 times 10 to the minus 4 divided by 1.17 times 10 to the negative 4. That will be equal to K2 over K1 and the concentration 0.45 divided by 0.39. What is the answer? All right, let us work it out.
Sir, I'm getting 1.15.
All right, you get 1.15. And how much you get for over here?
Sir, I got 1.11 for the
Sir, I
rate.
got the same 1.15.
All right, 1.15, right? Raised to the power of m. And then you would say m is equal to 1.15 divided by, so it is first order. Understand?
Yes, sir.
So that
Yes,
is
sir.
how,
Next question.
yeah, man. Right, let's move on to first one. All right, so let's go back to the,
Good night, sir.
let's go back to
Sir.
the original question. So we have calculated the order of the reaction, right? The first order with respect to S2O8, and we would have gotten second for I minus as well. All right, and you add them 2 and 1, that's 3. So the overall order would have been 3. Then it says calculate the rate constant. So to calculate the rate constant, you would choose an experiment. Rate is equal to K S2O8 2 minus times I minus squared. Transpose for K. K is equal to rate
Rate divided by the S2O8
squared. And all you do, pick an experiment. So I am going to use experiment number 1. And we're going to use the concentration and the rate for experiment number 1. But you can choose any experiment. So for experiment number 1, the rate is 1.4 times 10 to the negative 5. The concentration of S2O8 is 0.15. And the concentration of I2 is 0.25. And we must square that.
Sir, I got 5.8 times 10 to the negative 6.
How much I got?
5.8 times 10 to the negative.
Now let me try that again. 0.25 squared times 0.15. I'm
Yes,
getting,
sir, I got 5.8 as well.
so I'm getting 0.0094. That's a
Sure, that's
1.
what I got as well.
And 1.4.
Sir, I got 1.493 times 10 to the negative 3.
Thank you.
Me
That's,
too.
that's what I got, because I was wondering for a second if it was me. It's, if you're getting 5 point whatever, work out down yourself first and tell me how much I get. So the person's that got,
1.49, sir.
yes, I got 1.49 times 10 to the minus 3. When you work out down yourself, how much I get? So work out down here first. 0.25 squared.
9.38.
How much I get?
9.38 times 10 to negative
3. Right. So divide this now by that and see how much I get.
I got the 1.49
All
times
right.
10 to the 5.
Yeah, man. And then now, remember, it's K, so we have to calculate the units. Can anybody tell me the units? All right, let us calculate the units. Let me look at the table and see what the unit for rate was. It's moles per dm³ per minute. No, in this case, they put it in minutes. Okay. No, the comment section will not show. Yeah, let us calculate the units. So at the top, we have the rate, right? And the rate is moles per dm³ per minute. That is what was given in this example, in this question. Down here, this is concentration in moles per dm³. I'm working it the long way in case anybody does not understand. All right? Now, let me erase this. Where I have the multiplication sign, remember it would have been division, but then we have to flip it. So times, so mole over dm³, it becomes dm³ divided by mole. So it's basically like fractions. Times dm³ over mole and dm³ divided by mole. So this part of the question, or this part of the unit, is for I minus squared. That is where this comes from. And this one is for the S2O8 2 minus. All we have to do now is cancel. Mole cancel mole, dm³ cancel, dm³. That means we are left with what? dm6 mole -2 per minute.
Sir, what was the unit for the rate?
That girl is. The rate was moles per dm³ per minute. Somebody's mic is on. So this is the unit.
What was it for the concentration, sir? Just mole dm³?
Right.
Okay.
So the final unit is dm6 mole -2 per minute. Okay. All right, and then they asked us to calculate the initial rate when S2O8 is 0.13 and I minus is 0.32. Remember, we just calculated K. Now they're asking us to calculate the rate for specific concentrations. So the rate is equal to K. They give us the concentration for S2. All right, so rate is equal to S2O8, 2 minus I minus squared. So K is 1.49 times 10 to the minus 3. S2O8 is 0.13 and I minus is 0.32 squared.
Sir, what are we calculating here?
So the question said, calculate the initial rate of the reaction. Let me write it on the board.
Sir, are we gonna be moving on anytime soon, like to moles or transition metals or something?
Yes, we will go to moles. But if I see this tomorrow, make sure you can read it. I don't think this should be. And so that would be the question. Yeah, what the question? I hope where it's done that from. I don't think you're already not say that true. All right, so point
Sir,
3.2.
can the transitions please first before we go to most, because I feel like we're going to spend all
Please,
night
sir,
on.
please, please.
Point 3.2
Yes.
times 0.13 times 1.49 export -3. I get 1.98 times 10 to the minus 5. All right. Let's go to transition metal.
Yes, ma'am. Yes.
Sir, could you do group 2 after?
Group 2, that's basically just some trends to read. So it's kind of just transition metals, need a little explaining. And just to caution you though about rates of reaction, there's an next part about mechanism, but we will move on. If it comes, it's not a lot of marks. So yeah.
God will do the rest, sir. Yes, sir.
Yeah, man. I agree.
Which one, sir? What did you say? Isn't a lot of marks?
Reaction mechanism. Give me a second. All right, so I'm assuming everybody know from elements 21 to 30.
Yes. Yes, sir.
So just tell me them quickly. So 21.
Three, that would be scandium.
Scandium.
Then titanium.
Titanium,
Vanadium.
Then
chromium,
then manganese.
manganese,
Then iron.
iron, cobalt,
Cobalt, nickel,
Then nickel.
copper. Then.
Then copper.
Zinc.
Yeah.
What's the electronic configuration for scandium?
It's 21.
Short
It's 2. 1 is 2.
no, short and so we start at carbon. Remember with short and electronic configuration, they start at the nearest.
3D1.
Right, they start at the nearest noble gas, right?
There we do have the stars at 18, right?
If this say short and you start at
3D1 4S2.
Yeah. But titanium, it would be
3D2 4S2.
When I'm not exam na enough.
3D3. All right. So you should
Sir,
know.
so if you put the 4S before the 3D, it's wrong?
Well, for here, they put the 3D first. I noticed that on their book. So I follow it. All right. And normally, so you fill the 4S first, but the 3D, they place it first. So in terms of orbitals, the 3D orbitals comes before the 4S. It's just that yes,
So we pulled the 4S before we pulled the
you can check it. It's V or VA. V?
So
Yes,
we
no.
can put the 4S before the 3D, right? I don't think it's going to be incorrect.
Some sources are, depending on where you check, the 4S is placed before the 3D. All right. But on past papers, actually they put the 3D, then the 4S. All right. Yeah.
Okay, sir. Thank you.
All right. Now, when you're going to remove an electron, where you which orbital you take it from first?
4s.
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 4s, sir.
And you must also remember that you should be able to do the box method, right?
Yes, sir.
So if you put in the 3D first, that will be 3D, and that will be the 4s. So manganese, what's the atomic number?
25.
25. So 4s2, and we've filled the orbitals single first, right?
Yes, sir.
All right. So that is manganese, Mn. What would be the electronic configuration now for Mn, let's say, in the +4 oxidation state?
So it's going to lose
21.
So it's going to be 3d3.
21.
Argon 3d3.
So it's going to be argon, and then 3D. Right. So it loses the 2 from the 4s, then you start taking from the 3D. So you take the 2 from the 4s, then you start removing from the d orbital. All right?
Sir, if it is losing those 2 electrons, why couldn't it be argon 3D and not argon 3D3?
Because we still have electrons in the d orbital. So when it says +4, it is losing 4. And we take from the s first, then the d. So 2 comes from the 4s orbital, and then 2 from the 3d orbital.
Isn't that on 0?
Okay, sir.
On 0?
3d3. So the first thing I need to know, right? At least be able to write the electronic configuration. If that comes, it should be 3 marks. All right? No.
Sir, but we should write it for zinc and scandium.
No, if they ask for it, you can. What I'm going to say now, as I mentioned, zinc and scandium and zinc are not actually transition metals. Does anybody know why?
Them now
They don't have
Because they have a
incomplete
they can't form a stable ion.
So they don't have any incomplete 3D orbitals.
All right, so that's correct. So when transition metals form an ion, they must have partially filled d orbitals. Scandium atomic number is 21. Yeah, man, I'm going to do chromium and copper after this. So scandium, when it forms an ion, it is in the 3+ state. So Sc 3+. So if it's Sc 3+, does it have any electrons in the d orbital?
No, sir.
I remember we said transition metals, when they form ions, they must still have what? Partially filled?
The orbitals.
Right. So when scandium form the Sc3+ ion, it would lose the 1 electron in the d orbital, as well as the 2 electrons in the 4s orbital. Now for zinc, what is the electronic configuration for zinc?
3d10 4s2.
All right.
So we're going to get a periodic table.
Periodic table? No? Why need periodic table?
So we're not going to get a periodic table.
There's not do that over here. Yes, we get a periodic table.
Stop the capping.
Don't depress me, sir.
No,
Sir, not tonight. Not the night before the exam.
All right, I know you get a data booklet with certain values in it, but do you get a periodic table? I'm not aware of a periodic.
I was told that we will get a periodic table because remember we need the masses for certain elements.
No, they would give you the mass. Normally, when
No.
they give you it, the mass is provided in the question.
But sir, we need to know the atomic number for these elements. You may know them.
All right, let's say you will get it then. All right, let's hope you get it. But I mean, it's just 10 elements, not a lot. But yeah, all right, let's hope it come, all right? So it's argon, 3D10, 4s2. So when zinc forms an ion, it is forming the 2+ ion, Zn2+. When it forms Zn2+, it loses the 4s2 electrons. So is it partially filled?
No, sir, fully.
No.
Sir,
Right.
completely.
Exactly. So that is why scandium and zinc, they are not transition metals. All right, there's next thing now. We have to look at chromium and copper. There's something unusual about their structure, or in terms of how we write the electronic configuration. So just remember, zinc and scandium, they are not transition metals. All right, so chromium is 24. Can someone tell me the electronic configuration for chromium?
R3D5 3D5 4s1.
All right, the air 4s1 and the air 4s2.
Yes, sir.
All right, so your 3D for 4s1 and the air argon, what? It would be 3D4, 4s2. All right, so for the second one, that is what would have been expected, because we normally fill the 4s because it's lower in energy, then we go to the 3D. However, with chromium, this is not the electronic configuration. This one is, and the reason they say is that the 4s orbital and the 3D orbital is very close in energy. So let me just do the box method. 1, 2, 3. So if it was 4s2, 3d4, right? If this was the electronic configuration, they're saying no, these two orbitals are close in energy, 3d, 4s. So it is more stable if you place one of these paired electrons into the empty 3d orbital. So if chromium promotes one of the 4s electron in the 3d, empty 3d orbital, that is more energetically favorable. It is more stable to adopt the 4s1, 3d5 structure. So for chromium, yes?
What about the other elements that have like 3d3 or 3d2 with the 4s orbital filled?
So the point, this chromium, that is why the point was made about chromium, that the energy gap, specifically for chromium, the two of them are close in energy. So it's easy for chromium to promote one electron. Well, that's the reasoning that is provided, that chromium, the 3d and 4s orbitals are close in energy. So we could assume, right? So we could assume that the other ones where the promotion does not take place, the energy gap would be too large. All right. So in chromium, it's actually close. So we can promote one from the 4s to the 3D. All right, that is for chromium. For copper, copper is the next unusual one. What is based on the atomic number, what would you expect the electronic configuration for copper to be? So copper is 29, right? And if we follow the rules, what would have been the electronic configuration for copper?
3D10, 3D9,
3D9, 4s2, right? So this is what we expect it to be. However, the 4s is actually lower in energy than the 3D orbital. So for copper, you fill the 3D before you fill the 4s. So that is why with copper, it's 3D10, 4s1. All right. So in chromium, we actually promote an electron. But in in chromium, in copper, you fill the 3D first, then the 4s. All right. So that is why it is 3D10, 4s1. All right.
But again, please.
If I can say that again. Are you asking me to
repeat the part about the chromium, please?
All right, so chromium, it was paired, right? 4s2, 3d4. But the orbitals are closely in energy, so they can move of one of the electrons into the empty 3D orbital. So that is why it is 4s1, 3d10. Wasn't that 3d10? Sorry. 4s1, 3d5. All right, so that is why chromium is the 4s1, 3d5. For copper, you fill the 3d10 first, then the 4s. So that is why it's 3d10, 4s1. You fill the 3d orbital first because it is lower in energy than the 4s for copper. All right. So we explain why zinc and scandium are not transition metals, and we explain the anomalies with chromium and copper. All right. Now for transition metals, there's two things I want to do, right? We need to know in terms of explaining, because some things you can just read. But the part about, if you notice copper, and you must do this experiment, like probably in grade 11 or even in grade 12. What is the color of copper sulfate?
Blue.
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 Have you ever heated it? Have you ever heated it?
Yes, sir, and it becomes green.
When you heat it, what color it becomes?
White.
White.
Right. No, when you heat it, what is removed from it?
Zero water.
Exactly. So when water is there, right, it's blue.
Sir, can you repeat, please?
So we are saying that copper sulfate has a blue color. But if you heat it, the water evaporates and then it becomes white. That means when water is present, something happens that allows it to absorb water. When water is present, it causes something to happen for the iron to absorb light. Someone's microphone is filled with your praise. All right. Right. So if you notice, magnesium and aluminum, right? They just have a gray color. But when you get to the transition metals, chromium, copper, manganese, cobalt, they have colors, right? That's because they can absorb light. And I was using the example of copper sulfate. If you notice, copper sulfate has a blue color. That means it absorbs light. However, if you heat the copper sulfate, so copper sulfate, when it's blue, it has water present. When you heat it and the water is removed, so water evaporates, you notice it becomes white. So that means when water is present, something happens that causes the copper or the complex to absorb light. So with transition metals, we need to be able to explain why it can absorb light. So transition metals, they can form bonds with certain compounds, right? Those compounds are going to have a lone pair, at least one lone pair that they can donate to the metal ion, the transition metal ion. I'm going to write it on the board, so you don't have to worry. I'm just explaining first. So your compounds like water, they have lone pairs of electrons. They can donate it to the metal ion and form a bond with it. However, when that happens, right?
Can you repeat that, please?
So we have our transition metals like manganese, titanium, well, scandium is not one, copper, right? Those metals can form bonds with specific compounds. I won't tell you the name as yet, all right? They have a lone pair on them. They have to
the end of 2019. Yes, 2019.
Somebody's mic is on, just check a mic. All right, so transition metals, they can bond with compounds, we call them ligands. They must have at least a lone pair, all right, that they can donate to the transition metal. So when the ligand binds to the transition metal, we get a complex ion, right? Now I'm telling you, what I'm doing here is explaining why the transition metals can absorb light. And more than likely, you will see it tomorrow morning on the exam, all right? So the transition metals form colored complexes because they can absorb light. And the classic example I'm using is copper sulfate.
You're waiting, I'm writing. I'm writing what you're saying.
No man, I'm
Can
going
you
to,
repeat again, please?
well, I'm going to write it on the board after now. I'm just explaining first.
Thank you.
Okay. Right.
And before you move on, you were saying something about ligands, bonds, or something.
No, I was right. So you have a transition metal, right? They can bond with a specific compound. That compound, it has to have at least a lone pair. So that compound with the lone pair, we call it a ligand. So the ligand is the compound with the lone pair, or the ion with the lone pair. It binds with the transition metals to give what we call a complex ion. That complex ion, it is colored because it absorbs light. But how does it actually absorb the light? So remember, we have 5 d orbitals. 1, 2, 3, 4, 5. Yes?
This is going to be when like the electrons absorb the energy gap thing and they move to a higher energy level.
That is correct.
Okay, sir.
Yeah, man. So the d orbitals, right? The transition metals, they have their 5d orbitals, and they are
Sir, mic is mute.
Sir,
keep going on. All right. Right, so your transition metals, we have the 5d orbitals on one energy level, right? So all of them are basically of the same energy level. So we say they are degenerate. Now, when they form the bond with the ligand, it caused the d orbitals to split up. So before they were degenerate, meaning they are basically of the same energy level. When they form a bond with the ligand, it causes the d orbitals to split. Some go to a higher energy level than the others. All right?
Baby.
So they were on the same level before, and now they will not be. All right?
No.
Just a second. Right. So when the transition metals binds to the ligand, the d orbitals split up into different energies. And they pair up 2 and 3, right? To absorb light, the d orbitals, they must be partially filled. So if you have this, has anybody seen zinc powder before? It's gray, right? Zinc.
Yes, sir.
Right. If you remember, what is the electronic configuration for zinc?
There has the full shell, sir. Shell full.
3d10, right? It's d orbitals are filled, right?
Yeah.
Yes, sir.
Right. So if it is filled, can any of these electrons move up?
No, sir.
Exactly. So zinc is filled, so there's no room to absorb energy and go up. So it
And
must,
there wouldn't be any splitting of the orbitals.
right. So this, it wouldn't occur with zinc. So to absorb the light, you must have partially filled the orbitals. So what is going to happen? And also, not all the splitting, so in each transition metal is not like when they split, they are going to be in the same manner, right? So there are different energy gaps in each transition metal. So that is why chromium, it can be orange, manganese can be purple. The energy difference between the two gaps are not the same. Good. So your transition metals, it binds with the ligand, it causes the d orbital to split. And then now, the energy difference between the two orbitals, if the energy matches, so there's going to be a specific energy difference here. If it matches with the frequency of the light, the electron is going to absorb it and move on. All right. So the electron is what is absorbing the energy. So it can move. Yes?
So when we're referring to the energy that it is going to absorb, should we be specific?
No.
Just like visible light or something?
No, man.
Okay, sir.
Right. So all we need to know is that the d orbital split up is partially filled, so the electrons can absorb energy and move up to the higher one. And once it absorbs the energy, that is how it absorbs the light. And so that is why transition metals, they can form colored compounds. Electrons in lower energy d orbitals absorb light energy and move up to the higher d orbital. All right? So that is how they form the colored complexes. All right? So let's just run through some stuff that you should also know about transition metals quickly. All right?
Sir.
Yes.
So you're going through the equations. And like the name of the compounds and so on.
The octahedral complex.
No, like not that, I mean like going from like the formula of the different compounds. And like the name of it, like the formula of the different compounds.
And the ligand exchange. Yes,
yeah,
I'm
like
going
that,
to
and like the name of them. I think we need to know the name of it.
Yeah, I'm going to do it quickly.
All right.
Yeah. All right, so I have made little jottings here for you. All right. So you should be able to at least tell some characteristics of transition metals. So these are some characteristics of transition metals. All right, just take off this and then we look at, and then I write why they are able to absorb light.
Sir, is that supposed to be more than one oxidation state?
Yes, from compound with more than one. Yeah, more than one. Anybody else is still writing? All right. Yes, I can continue now.
Yes, sir.
All right.
Sir, that's the explanation for what you were explaining before?
That's what I'm going to do now.
Sir, so what was on the board?
Just some characteristics of transition metals.
Okay, sir. I know you're going to write about the color thing.
Right.
Okay, sir.
I can erase the first point.
No, sir.
All right.
Sir, hold on. You're really now, sir.
Yes, I can.
Hey, hold on.
No problem, no problem. I want to show you how to calculate empirical or molecular formula, just in case.
Sir, observes what?
Yes, sir, man.
The orbital observe.
No, I'm not finished. I want to erase this.
You can do it now.
All right. All right, so the electrons in the lower energy d orbital observes.
Sir, when it gets excited, that's when it exits its ground state, right?
Please repeat.
When it gets excited, it exits ground state, right?
That is
This
correct,
its
right?
lowest.
Right. And so this is the final one. So you don't have to swap it like word for word. Just remember, in a complex ion, the d orbitals are separated into two different energy levels. The electrons in the lower energy level, they can absorb light and move up into the next one. That's basically it. Is anybody still writing?
sir.
Yes.
Sir, where you have lone pair of electron that can form.
And hard, that's it.
I can erase my right. All right, so we're going to look at the complexes. So some of them, the most popular one is 6 coordinates. So your metal ion, it can form a certain amount of bonds with your ligands. But the term, depending on the size of the ligand, determines how much of them can hold. So like water and ammonia, those are small ligands. So for this one, we can fit 6 water in the complex with iron. The reason why it is a 2+ charge, water is a neutral. No, you don't use VCPR here. The water is a neutral molecule, so it's only the charge and the Fe2+ ion.
Sir?
Yes? Also remember the lone pair, so the reason why it's the oxygen, because it's the oxygen that has the lone pair. All right.
So they're supposed to be 90 degrees apart, right?
For octahedral?
Yes, sir.
So,
The bond angle is supposed to be 90 degrees?
no, it's not VSE pair.
So since you have to ask them for the angle.
What were you asking about dotted line?
like some broken lines from, I think, the water to the iron.
You don't have to use you don't have to be a broken line.
Okay, sir. Thank you.
So, sir,
Alright.
you're supposed to indicate the 3 dimensions, right?
If you're supposed to,
Indicate the 3 dimensions.
as in?
Like using wedges or dotted line.
No man, I can't for that. No man, yeah, we keep it. No.
Okay.
If you want to, as in, you don't need to. Right. So at this level, we don't need to show the we don't need to show 3-dimensional structures. So for the coordination complexes, right? You have coordinate, you have the octahedral, that is when you have 6. And it's very popular. We can have 4 as well, that's tetrahedral. And so coordination is 6 complex. Remember the charge on it is coming from water not having any charge. And this is iron in the 2+ oxidation state. So it's just a 2+ charge. With the coordination complex of 4, that is an example with like chloride ion. So let's do the chloride ion. Copper. All right, if this is Cu2+, can anybody tell me what will be the charge? What should be the charge out here?
2 minus.
2 minus. Can you tell us why it should be 2 minus?
Because each chloride is -1, C is 2.
Right. So we have 4 negative chloride ions, and the 2+ and the copper cancels 2 of them. So the overall charge on this is 2. So we have 2, 4, and 6. So 6 is octahedral, 4 is tetrahedral. What is 2?
Linear.
Linear.
Yes, linear.
Sir, can you repeat the question, please?
No man, we're just looking at these shapes of the complex ion. So we have done 4, we need 6, and we are doing 2. So when it's 2, the shape is described as linear.
Sir, can you
Yes.
repeat why it has a 2 negative charge?
All right, so we have 4 chloride ions here, right? So 4 chloride ions, that is 4 negative charge. And then this is copper in the 2+ state. So -4 plus +2, that is -2. All right?
Oh, okay.
Yeah. With water or ammonia, those are neutral molecules, so they don't carry a charge. And so when it was with Fe2+, because the water is a neutral molecule, then the overall charge is just 2+. Right? And just as a cool side note, right? Even when we're doing like reactions and we write Cu2+, for like copper sulfate, it's not actually just the Cu2 plus. Those are complex ions. So it's just to simplify it where we put Cu2 plus. Because as you can see now, copper, when it's blue, as you know now, it is it's a complex ion, right? When it is blue. So writing Cu2 plus technically is not the correct formula for copper because it's in a complex ion. The naming, we don't need to, it's the complex that we need to know to draw. I didn't see anything about the naming of the compounds.
Sir?
Yes?
Isn't copper tetrachloride yellow? Or whatever it be called, isn't it yellow?
I don't remember exactly if copper, no man, but copper chloride, number one, copper is in the blues, sorry, is in the 2 plus state that is normally blue, but when it's with chloride, I'm not exactly sure of the color. But when it's with water, it's blue.
I think it's yellow green. And then cobalt is
And with chlorine, it might absorb a different light.
Yes, sir.
Sir, I think cobalt is cobalt chloride. The COCl.
Cobalt chloride.
CL4 is blue. And CuCl2.
CuCl2.
CuCl4 is yellow green.
CuCl2. That's what you said?
I don't remember which one it is, but when
No, sir.
it's bonded to copper, it's yellow green.
The coordinate bond, the one that you have shown right here. That's yellow.
That's yellow green.
Yeah.
All right. So just let's do the linear one. And then after this, we just do the Ligand Exchange. And right there, so I really need to show you a little more. All right, so we're going to do this and then the Ligand Exchange reaction. What would be the charge on this? So ammonia, it's a neutral molecule. It doesn't have a charge. And silver is +1. So silver is Ag plus. So the charge on it would be plus. Okay. So just remember water. Let me give you some examples of ligands. Right? So simple ones. But just remember water and ammonia, these are small. All right, so let's say you're asked to draw something, a ligand with water or ammonia, you can use 6 of them. But chlorine, the chloride ion, is a bigger one, so you would use 4 chloride ions. All right, these two, they are small, so they can form octahedral complexes. The 6, the one with 6. All right. So water and ammonia, these two ligands, they are small, so you can fit 6 of them. This one is larger, so you can fit 4 of them. All right. So linear, you just need 2 of your ligands. Tetrahedral, you need 4. No, we're just saying that, so water, so if you look, when we did water, right, we use 6. And when we use the chloride ion, we do 4. It's because the chloride ion is a bigger ligand, so we cannot fit 6. But water and ammonia, they are smaller, so more can hold. So that is why for the octahedral complexes, you will see like water and ammonia. But for tetrahedral with 4, we use the chloride ion because it's 4 of them that the most we can use is 4. What's the coordination number for this? Anyone know what's the coordination number?
Sir, in the state it's in right now,
Yeah.
0.
When the shape is octahedral, what's the coordination number?
6.
And when it's, hold on, 6, is it 6? Right.
Yes, sir.
So the coordination number is just the number of bonds the ligand is forming with the central metal ion. So this one, we are forming 2. So the coordination number is 2. We're forming 4, the coordination number is 4. And for the octahedral, the coordination number, it would have been 6. All right. There's one last thing I want to show you, is the ligand exchange. How the time is going? Ligand exchange.
Sir, you're still going to the empirical formula?
I want to, honestly, so, all right, let's just hurry on with this. Let me just put a reaction on the board and tell you what happens in ligand exchange. I'm going to post a transition metal pulse paper question in the morning so you can look out for it. All right. I'm going to look for one sometime early in the morning, work it and post it. So, and I need to answer one for buffers. So I'm going to do one for buffers and transition metal. About 5, 6 in the morning and then post it. All right, so for Ligand Exchange, right.
Right. Picking up every time. I'm gonna prepare.
Someone's mic is on. So in ligand exchange reactions, you will see a color change because one ligand is replacing the next one. So remember, if the ligands switch, the level at which the d orbital split will be different based on the ligand that is present. So if you have cobalt and water in the complex ion, you have a pink color. But if you add hydrochloric acid to this, it will change to pink. not pink, sorry, it will change from pink to blue. So when the chloride ion is present, it's blue, but when water is present, it's pink. No, yes?
If we added hydrochloric acid, it would be blue as well, right?
No, it is the hydrochloric acid that we add. So the hydrochloric, the hydrochloric acid is the source of the chloride ions. No, so what happens when you add the hydrochloric acid, it pushes, so if you notice I use 2 arrows, it would be an equilibrium reaction, right? So what would happen if you add a lot of water to this reaction?
It will turn back
pink.
It will turn back pink, exactly. So in a ligand exchange reaction, it's simply a stronger ligand, or so this ligand would have to be a stronger ligand than water to displace it. So in a ligand exchange reaction, as it says, it's just one ligand displacing the next one. So you get a new complex ion being formed. So that's where it says ligand exchange. So you have your complex ion, which is the transition metal, and the ligand. And we're adding a next ligand to it that can displace it. And once it is displaced, yes?
This would explain the experiment for when hydrochloric acid and ammonium is added to the copper and the cobalt, right? The ligand exchange.
When hydrochloric acid was added to, which one?
The copper and the cobalt.
The copper and the cobalt.
Sir, on the syllabus, there's an experiment that is required for ligand exchange, and the addition of hydrochloric acid to copper and cobalt is one of the ligand exchange and the hemoglobin.
So this one would be cobalt.
Yes, sir.
Hydrochloric acid to it. So what we, all right, so for the chloride one, it would be this, so if it's copper, it would be copper and the chloride ion. So we would just need to look at the color. Let me see if I have it here. With copper and chloride, yes, with copper and chloride, it would give you this green, a green color. So it's the same thing. So this one is cobalt, so let's do copper. It's the same thing, right? All we're going to do is replace the water with chloride ions. And the source of the chloride ion, as I said earlier, is hydrochloric acid. Right? Where is it? With copper. Right. So you have copper with H2O. Right? And if we add the chloride ions, I'm going to put the complex here. So we will get CuCl4 negative 2 plus the 6 H2O. Now we know that when copper is with water, it has a blue color. But when it is with chlorine, this looks green. Okay. Yeah. It says olive green or yellow. So it's describing this as olive green. I don't know what green is that, but it says olive green or yellow. All right, so when it's way to, so the color change for this is from blue to yellow. So if this is what it had asked for, then these are the two reactions that you just must remember. So with cobalt, it's from pink to blue, and when it's with copper, it's from blue to yellow. And just remember, all you're doing, if you ask for the equation, you're just replacing chloride ions with water. And remember, water is a small ligand, so you can fit 6. But the chloride ion is a bigger ligand, so you can only fit 4 in it. All right. So you should get CuCl4 or COCl4. All right. All right, so let's do, I'm going to do the money clock. It's 10:30. I should have stopped already, but let me just do the empirical formula quickly. All right. I will do a
Are we
question.
getting qualitative analysis?
Well, it wasn't on the topic. It says transition metal and group 2. Well, transition metal can come because transition metals can work, but it wouldn't make sense because transition metals are colored compounds. And once you see the color, you would know which transition metal it is. If it was like
But
with
sir,
aluminum or lead, it would be
so
a
you know,
lead.
so you know, somebody I go through some of them possible questions there, so them have some call up some transition metals. And I say, how am I know them code? I'm looking at the book and I can't find some of them code at all. Google me, I forgot one.
Send the paper to my email. I'm gonna write it down.
All right.
Yeah. I'll put it there. So we can work it in the morning.
So when you're testing for the presence of water, what do you do to see if the water is present?
The cobalt chloride paper.
Any more extension?
The cobalt chloride paper. All right, guys, quickly, let me show you the empirical formula question, and then I have to close. Because I have some other stuff to start with. Where was it? All right, so with the empirical formula, it's
Real dot chemist?
yeah, 92 at gmail.com. All right, so
Sir,
yes, you can go ahead.
sir, when we're doing the calculations tomorrow, should it be in pen or pencil?
If it should be what?
Pen or pencil.
They're showing some, but say just the motivator showing us that tape is not fixed. The list will have that represent the region. One of them have 5. Right.
Five what?
There was
Repeat that. Repeat that.
the highest was a 2.
Oh, what?
That school, me mean in the Caribbean for that subject.
The highest was a grade 2. I'm not following. I can just repeat.
And if you say you might talk on say honestly.
Oh, probably.
I wish topic this, sir.
It comes under moles, but yeah, it's empirical. It's calculated empirical and molecular formula. So I'm just going to do, but it's called combustion analysis. So you are going to burn a hydrocarbon, collect the mass of carbon dioxide and water, and use that to work out the empirical formula. All right, so that's the question where you're supposed to calculate the empirical and molecular formula. You will do this type of question again in Unit 2. So this is actually one from Unit 2, but it's the same question, same type of question for Unit 1. You will get the mass of carbon dioxide and
So moles na Unit 2, sir?
that, yes, not the typical mole concept, but just this part of it, just this specifically. But titration is there as well. All right, so as soon as I finish, right, you'll let me know. And just as I have to advise, don't try to study, just ensure you have 2 modules covered. All right. Probably module 1 is the easiest bet, and 3. I would tell you to study module 3, Transitional Metals, and group 2.
Module 2 are the easiest to me, sir. No lie.
Module 2?
Same.
Module 2?
Yeah, module 1 having moles. Me I like moles.
But rates supposed to good thing, but yeah.
I like chemical equilibrium with the hardest in module 2 because they hard about equilibrium and concentration. If you find kind of confusing more. But buffers easy too.
Yeah.
Sir, ice metal will be my downfall skills.
All right, just remember, for ice method, the only time you use it is if you don't have everything at equilibrium. So if they give you everything at equilibrium, you don't need to use it. Is when you don't get everything at equilibrium, then you use it. All right, let's just knock off this one. So if you have to calculate empirical formula, given the mass of CO2, all right, you're going to need, so in calculating the empirical formula, you need the mass of carbon, you need the mass of hydrogen and oxygen. Hold on, let me check if it actually contains oxygen. Carbon, hydrogen, and oxygen, right? So to do this now, we need the mass of carbon, we need the mass of hydrogen, and we need the mass of oxygen. We are going to get the mass of carbon from CO2, the mass of hydrogen from water. To do, because in the interest of time, just know that if you want the mass of carbon, you put the atomic mass for carbon over the molar mass for CO2. So it's the atomic mass for carbon, relative atomic mass, over the molar mass. So 12/44 times whatever mass of CO2 is given. What is the mass of CO2 from the question?
2.3.
So what are we working out? The molecular formula?
No, empirical. To get the empirical formula, they gave you the mass of CO2 and the mass of water. But in calculating empirical formula, you need the actual mass of carbon, not CO2. So to get the mass of carbon, it's 12 over 44 times the actual mass given for CO2. The 12 is the atomic mass for carbon, the 44 is the molar mass for CO2. All right, and if you do that, you should get
0.62.
how much?
0.62.
All right, 0.62 grams. So this is the mass of carbon. To get the mass of hydrogen, the formula for water is H2O. So we have 2 hydrogens present. So it is the mass
2 over
of
18.
hydrogen, right, 2 over 18 times the mass of
0.93.
Right.
Zero 0.103.
0.103 tons. Now to get the mass of oxygen,
We have
the mass
16 over 18.
we're gonna do it that way. But the reason why, because oxygen is actually a reactant. So remember, in combustion, we are burning the hydrocarbon in the presence of oxygen. So to actually get the mass of oxygen, we are going to, so the mass of the sample, let me just do this here. To get the mass of oxygen, it's the mass of this sample minus the mass of carbon and hydrogen. So you're going to add up the mass of carbon and hydrogen and subtract it from the mass of this sample. The mass of the sample was 1 gram. So 1 take away 0.103.
You think of the 50 grams that they put, sir?
No, that's the molar mass for the compound.
So where they put the mass of the sample was 1 gram. Did you write that down?
Is it
0.483.
So did you write that the mass of the sample was 1 gram?
Yeah, man, just read bucket questions somewhere in the middle.
0.483, sir.
0.483. Oh, hold on. When you add it up, let me 0.62 plus 0.103.
0.277 may I get?
0.723.
0.277 may I get?
All right, 0.277. All right. So we have the mass for carbon, mass for hydrogen, and the mass for oxygen. Now, if the question, it can do this, where it just give you the mass for carbon, hydrogen, and oxygen. Or it can give you the mass for CO2 and water. And you will have to first calculate the mass for carbon, hydrogen, and oxygen. So once we get the mass,
when you finish,
So can you just put 1 over 18 times 0.93 to calculate the mass of oxygen?
If you
could just put 16 over 18 times 0.93 to find oxygen, no?
18.
Yeah, could you do that?
No, that won't work.
Oxygen also in a CO2.
Oh, I see.
But in this case, in this say it I use as a reagent.
So the first step in actually calculating our empirical formula is to calculate the moles of each of our elements. So remember, mole is mass divided by molar mass. Someone another question?
Sir, we wouldn't use the RMM, which is 58.
No, not yet.
Oh,
Remember,
okay, sorry.
they gave you the molar mass of the compound. We don't know the actual formula of the compound as yet. The reason why we get the molar mass of the compound is to calculate the molecular formula, not the empirical. All right, so we're going to calculate the empirical, then the molecular. All right, so 0.62 divided by 12. That is, I'm getting 0.0517, 0.103, and 0.277 divided by 16. I'm getting 0.017. All right?
You can divide all of them by the smallest.
That is correct. So we would divide by 0.017.
So what were you calculating before all of this?
Please repeat.
What were you calculating before you found the
We
mole?
were calculating the mass of carbon from the mass of CO2, the mass of hydrogen from the mass of H2O.
Mole equal given mass over molar mass.
How much you get for this?
6, sir.
6, all right. And this is 1. So the empirical formula is C3H6O. That's your empirical formula. To get the molecular formula, you are going to calculate the mass of your empirical formula. All right, so 12 trees, that's 36. 36 and 6, that's 42. 42 and 16, that is 58.
Yes, I know you guys the 58, right? And
Right. So we're going to calculate, just let's call it N, right? And N is the molar mass of the compound divided by the empirical formula mass. All right? The molar mass, they said, was 58, and we calculate our empirical formula to be 58 as well. So 58 divided by 58 is 1. Right? But for explanation purposes, we're going to change the molar mass of the compound to 116. So 116 divided by 58, we would get, right? So N is 2. So to get the molecular formula, you are going to multiply your empirical.
Wait, what on there? What the 116 come from again?
Sir, the 116 applies for all.
No, wait.
No, just use it as an example.
Oh, okay, thank you.
The question, it was 58, but we are going to get 1 for the answer. So I'm saying for explanation purposes, I'm going to change it to 116 so that I can get 2 for the answer. So 2 now, what we are going to do is multiply the empirical formula by 2. And so your molecular formula, so 3 times 2, that is 6. 6 times 2, that is
12.
12.
Or 2.
1 times 2, that is 2. Right, so this would be the molecular formula. If N was 2, but in this question, N was 1. So the empirical formula and the molecular formula would be the same. All right, so let's just go again. This is combustion analysis, where you burn a hydrocarbon, you get carbon dioxide and water. To get the mass of carbon, is 12 over 44, the mass of carbon over the mass of CO2, times the actual mass that is given in the question. Right? So let's say it was 1.5. That's what you do. That is how we got the mass of carbon. For hydrogen, it is 2 over the mass of, over the molar mass of water, which is 18. So it's 2 over 18 times the actual mass of water that was given. That is how we get this. And then oxygen, you add up the mass of hydrogen and carbon and subtract it from the mass of this sample. That is how we get oxygen. Good. Now, once you get the mass of each of them, you start now by calculating the moles. Notice here for hydrogen, I am not using 2 because we are not dealing with water. We are dealing with the mass for hydrogen, which is 1, right? And so you get the moles. Once you get the moles, you compare them, right? See which number is the smallest and divide through by it. And we get 3, 6, and 1. That's your empirical
Sir, are
formula.
you going to be at school tomorrow?
Yes.
Okay.
Come on.
Which school is that?
Marlborough.
Sure.
All right. So I really have to close here, unfortunately. But as I said, I'm going to upload a question for transition metal, one for profiles, and one for which topic? I'm going to look for equilibrium.
Sir.
Yes.
Sir, I have one more question. Sir, how do you find the number for N? The number
For N?
yeah.
Oh, for N, they will give you the molar mass of the compound in the question.
Okay.
And then you add up the empirical formula mass. So the empirical formula mass, that was 58. In the actual question, the molar mass of the compound, it was also 58.
Yeah.
So the
I get
answer,
1.
right? And so 1 times this
It'll be the
would
same
have
thing.
gone back the same thing, which is C3, 8, 6.
Empirical formula. Let's go back over moles.
All right. Thank you, sir.
Sir.
Sir, excuse me, sir.
Suppose when you work out the moles, you get like decimals in the.
Let's say you get 2.61. When you're doing empirical formula, you're welcome. All right, so when you're working out empirical formula, the rounding off, like when it's normal, it's like 0.5 or more, you will round up. That does not work for empirical formula. It must be close to a whole number for you to round up. So it must be like at least say 2.75 or more, because it must be close to a whole number. So 2.75, 2.8, 2.9, that is when you can round up because it is close to 3. But anything like 2.5, 2.6, you don't round up.
All right, sir, suppose.
Just a second. What you will do, you are going to first times it by 2. When you times it by 2, so let us just do it. 2.75, 2, I get 5.5. So when I times this by 2, I get 5.5. I still cannot round off 5.5. It must be close to a whole number. So next, I am going to try it with 3. So I'm going to say 2.75 times 3, and I get 8.25. Now 8.25, this is close to 8. So I can this is 8. That would be H8. Right? So how do you know when to round up and when to round down? If the decimal is below 3, so if you get something below 3, so as long as it is 0.2 something or below, then you round it down. So if you say 2.36, do not round it off. All right?
Sir, question.
Yeah.
When I multiply it, you multiply everything by the 3?
That is correct. So not just the hydrogen, you will have to multiply by carbon and by oxygen. There's a question.
And the hydrogen was 2.25, I can multiply by 4 to get C4H9.
No, if it was 2.25,
yeah,
No, 2.25. So once you get something below 0.3, you can run it down. So 2.25, it is close enough to 2 to round off.
Empirical formula, I can understand, yeah.
No, I'm saying, so normally we say when it's 0.5 or more, you round up. And when it's less than 0.5, you round it down. But for empirical formula, you want the decimal to be close to a whole number. So we're saying 2.4 is not close enough to the whole number to round it down. Even 2.6 is not close enough. So you want answers like 2.15 to say 2.15, that's approximately 2. You get what I'm saying?
Yes, sir.
When you go to 2.35, don't round it off. It is not close enough. All right?
So in the case of 2.5, you multiply by a number, forget a whole number.
No, so that is why I was trying to give you a number to use. So I'm saying once it's below 0.3, you round it off.
Okay.
Yeah. And if it's 0.75 or more, you can round it up. But not when you're getting like 0.3 something, 0.4, 0.6, you don't want to round it off. Right?
Yes, sir. Thanks.
Yeah, man. All right, so I'm going to close it here for tonight.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Bye, sir.
All right.
Bye. Thank you, sir.